Hello, everyone. I'm going to come back to these smoking pests a little bit later. And I'm going to start by saying um, that you smell. I'm just going to go ahead and say it. And every single one of you smell, some more than others. And it's not surprising that kind of has a slightly offensive connotation because smell really does have a bad reputation. We instantly think it's a bad thing, a pong, a stink, a whiff, a stench, something feeling foul, putrid. And that sense of disgust that comes with smell is an important survival mechanism to prevent us from, for example, eating something bad and getting sick. But smell can also be really good, and there is a hidden language of scent being used all the time. In humans, for example, we all know that we're not supposed to mate with our close relatives, let's say. And they did an amazing experiment where they gave out t shirts to a group of men and asked them to wear them for a number of nights. They collected those t shirts in and gave them to women and asked the women to smell those t-shirts and choose what smell they liked the best. And interestingly, the smell that they liked the best came from the person who was most genetically different to them. And so it plays a big role in a hidden world that we don't really even think about. And where I work, we are unlocking that secret language of scent. And it really matters because the future of pest detection is data driven. And we'll come on to that, I'm sure, and in another talk as well today. And some of the best solutions have been right under our nose all this time. But before I talk about that, I want to articulate one of the biggest challenges facing the pest control industry at the moment. And I know there are several of them, but increasing pest volatility, so changes in pest patterns, is what we're seeing. And we will see more of it in the future, driven by climate change, so warming temperatures, and insecticide resistance. So here you can see a picture of the Asian tiger mosquito, which can transmit diseases like dengue and yellow fever. It's found, it's been for several years now, it's been found breeding in parts of Kent and the southeast. And as yet, our winters are still cold enough that it can't overwinter. So the UK Health Security Agency has declared its status as detected, but it's not yet established. But it is established in France, and that's relatively recent. It's been moving northwards from the Mediterranean. And that's one of the reasons why, particularly the Asian tiger mosquito, is such a threat. It's because its eggs survive desiccation. So the eggs could be laid on a tire, for example, in the south of France, and left untreated. That tire ends up over here in the UK, and then with enough rainfall, enough a pool of water is all that needs for the egg to hatch out and turn into a group of adult breeding mosquitoes. So a few more examples. Loss of winter kill in rats. So since the 80s and 90s, we now have year-round rats. The harsh winters used to reduce the rat population, but no longer. Now rats breed throughout December and January and lead to spring population increases in cities like London and Manchester. Resistance to insecticides. So here you can see two lovely bed bugs. We all remember the all the media hype a couple of years ago about bed bugs, but they've developed resistance to insecticides and they're being spread through global travel. In particular, we see bed bugs in travel interchanges. Um, and they're developing, or they have developed genetic knockdown resistance, developing these thicker exoskeletons, their cuticles, making them immune to some sprays, and also behavioral resistance. So things like the German cockroach with glucose avoidance, rendering some baits ineffective. A lovely picture of a couple of Asian hornets. The expansion of invasive species is something I'm sure some of you are experiencing, and it'd be great, put anything on the chat if there's another species that you're kind of coming across or that you're concerned by. But warmer climates are essentially opening the door for species that previously couldn't survive in the UK's temperature. So I mentioned the tiger mosquito already, but the Asian hornet's definitely moving into the UK as a threat to honeybees. Other examples are the oak processionary moth. So that caterpillar forms these big mounds of caterpillars in oak trees and becoming quite common now in London parks, and it's moving further northwards. And tropical invader ants like the faro ant and ghost ants thriving in heated urban areas. Another thing that happens with warming temperatures is shorter breeding cycles. So obviously insects are ectothermic, they're cold-blooded, meaning that their metabolism and reproduction speed are directly related to external heat. So for example, when you get a 2-degree increase in temperature, some species can fit 1 up to 5 additional generations in a single season. So an example here, you can see the picture of the housefly, but populations in the UK of the housefly are expected to increase in extreme heat. So for example, 37 degrees, which now is, we are seeing those temperatures. A housefly egg that normally takes 20 hours to hatch can hatch in just 8 hours, and larvae become adults in only 4 days. So you're probably wondering why all of this has, or what all of this has to do with scent. And this will become clear. Because what I've just described is how unpredictable pests are becoming, or pests can be. And how can we take control of that unpredictability and make the unknown known? And that's why the future is of, when I'm talking, near, but also far distant future, is data-driven pest control. So I can't pretend to know, obviously, about running a profitable pest control business. That's your jobs. But all roads right now are leading to more data-driven pest control. So if you know what species is a problem, exactly where it is, when was it and when is it there, and how many. So sometimes how many is important. Sometimes one is too many and you might have to react to one incident. Sometimes population dynamics are more important to know, and there's threshold levels that are tolerable. With this information, we're able to put ourselves in a better position to be able to respond efficiently and effectively. And part of that, the data-driven future, is accurate pest detection. Accurate pest detection is key. In 2026, really good pest detection is basically a number of things, 5 things. So moving from a reactive to a predictive position. So the old way, and probably still quite common way, is, to visit a site and find the infestation and kill it. And this is a challenge if you're chasing a problem, and takes obviously quite a lot of time. New detection methods, AI-powered sensors, like Spotter for bedbugs, Secure Choice, and we're developing a product as well, which I will talk about in a minute. They monitor 24/7, so obviously don't tell you that there is a pest, they tell you exactly when it arrived. So by catching a single scout, for example, a scout rat or one bedbug before it breeds, you avoid the massive kind of clean out jobs that require multiple visits with a single trap or a small spot treatment. So we're moving to point 2, digital proof of absence. So like the new product, the biggest shift is that now companies are starting to charge for the absence of pest, and that is a huge change to business models, rather than charging for the act, or as well as charging for the act of killing them. So detection allows you to keep high-paying contracts active using non-toxic methods, monitoring methods, And then you're also selling guaranteed compliance and audit readiness. Then moving on to targeted treatment and prevention. So instead of spending a long time looking for where the problems are, automated and well-placed and accurate detection will allow more targeted treatment. So only traps 4, 12, and 44 have activity, for example. Um, and then climate adaptive heat mapping. So because of the unpredictable outbreaks like the recent surge in bed bugs, it can, I think, make make it a challenge to manage profitability. AI systems are being developed that will analyze environmental data as well as sensor data to create infestation heat maps. And I don't think we're quite there yet, but it's definitely where the industry is going. And then also, detection plays a huge role in managing chemical resistance. So it's a crucial part of integrated pest management, obviously, knowing when you have, and where you have, and what pest. So when you have accurate detection, this allows technicians to be snipers rather than blanket controllers. So where does the sense science come in? And as I said at the start, the future of pest detection is data-driven, whether we like it or not, and some of the best solutions have been under our nose. Scent detection is clearly not new, but it is an underestimated science. We're all familiar with this lovely nose and how well dogs can smell, detection dogs being used obviously to detect bed bugs. And a dog's brain is about 40 times, the smell part of their brain is about 40 times greater than ours. We, when we were at the London School of Hygiene and Tropical Medicine, were helped run the UK study for canine detection of COVID. We collected odour samples from about 4,000 participants, some with COVID, some with symptoms, some with no symptoms, some without COVID. And we were able to identify a really specific scent associated with COVID infection, even in asymptomatic cases. So we're able to understand what is that odour chemically, and also train dogs, working with medical detection dogs to be able to detect it. But insects are even better sniffers, but they smell in a different way to dogs. So on the left, you've got the dog, which is a high definition scanner. On the right, you've got the insect, which is more of a laser focused sensor. So dogs' systems are built for volume and process power. So it builds a scent picture of the world. And they have more of a scent memory. So dogs are incredibly good at being able to distinguish between complex bouquets. I like this example because it says dogs don't just smell the stew, they smell the beef, the carrots, the specific type of pepper in it, and the person who cooked it. Insects, on the other hand, have a much smaller system, but it's really well tuned with extreme precision. So they use sensilla on their antennae to kind of catch molecules. So while dogs have more receptors, the insects' receptors are more specialized. A male silkworm moth, for example, can detect a single molecule of a female's pheromone. And it just a few molecules hits its antennae, and that causes a behavioral response. It will fly upwind towards the source of that odor. And so the purpose of that in insects, the insects don't explore with smell like dogs might. They react to it. Their smell is a set of if-then triggers. If a pheromone, then mate. If CO2, for example, then bite if you're a mosquito. If glucose, then eat if you're a cockroach, unless you're an averse cockroach, of course. This is an amazing example of using honeybees as bomb detectors. So they were trained in a kind of Pavlovian way where they provide honeybees a sugary reward when they correctly identified an explosive. So when they identified the explosive, what happens? They stick their tongue out, as you can see in the right picture there, which then breaks an infrared beam, setting off the trigger. It's not a particularly scalable technology, but it really demonstrates the amazing power of insect intelligence and scent science for detection. And how does it really apply then? So 2 ways. And it all comes down to the important role that smell plays in an insect and mammalian behavior. So tools for attraction, really, really important for understanding how odor relates to how pests find each other, how they find food, how they send a warning signal even, and semiochemicals play a huge role. So this is a bit of the techie bit, but it's really, really important to understand the different types of attractants that are out there on the market and how you use those best in attraction for traps, for example. So semiochemicals from the Greek semion, meaning signal, they're the chemical languages of the natural world. They are organic compounds emitted by one organism that trigger a specific behavioral or physiological response in another. Two main categories, and it depends on who is talking to whom and who benefits from the conversation. So on the left there, you've got pheromones. So pheromones are signals sent between members of the same species, and they come in different varieties. You've got sex pheromones, for example, those that are used by a female moth to call a male moth to mate. An aggregation pheromone used to signal a good food source or a safe place to hide, common in cockroaches and bedbugs. Alarm pheromones used to warn others of a predator, so aphids on a leaf, for example. One may alarm and then all the aphids drop off the leaf. And then trail pheromones, so ants use these, for example, to create a highway which shows the other ants where the sugar or water source is. And then you've got allele chemicals. So these are chemicals that are signals sent between different species. Chiromones, for example, benefit the receiver. An example would be a mosquito smelling CO2 and lactic acid from our skin. The mosquito gets a meal and we get a bite. So there's a bit of a one-way relationship there. Alamones benefit the sender. So an example would be a flower emitting a scent to attract a pollinator, or a stink bug emitting a foul smell to deter a bird. And then you've got cinnamones, which benefit both. So, for example, when you've got a plant being attacked by a caterpillar, the plant might attract a chemical that attracts parasitic wasps that will then lay its eggs inside the caterpillar and ultimately kill the caterpillar and help the plant. The ones in blue I've highlighted because they're often used in attractants for insect detection. And I'm going to talk through a specific example because we are a team of, I guess, chemists and entomologists who have worked quite a lot on particularly a bedbug attractant. So here I've put the title of the academic paper where we found the specific role that bedbug poo basically plays in attracting bedbugs to the refuge. So the bedbug poo contains the aggregation pheromone that bedbugs release. So, and you can see these pictures here are an extract from the paper by Dr. Weeks, and also on there are the co-founders of the company that I work for, Arctech Innovation. So you can see on the left there, that's a Petri dish seen from above, and there's two odor pots. In one odor pot, there's no odor. In the other odor pot, there's the bedbug poo, basically. And you can see on the white lines is the activity of the bedbug in that Petri dish, and it's really, really concentrated to the odor. On the other side, neither pot contained an odor attractant, and you can see the white lines of where the bedbugs have moved, and they're really all over the place, basically. So when a bedbug is hungry, it's searching for a blood meal. It follows chiromones. It follows CO2 and other volatiles emitted by a person. When it's looking for somewhere to hide, it follows the bedbug aggregation pheromone, which is naturally found in poo. So this was the paper that basically said there's a really strong attractant in this poo, and that's what bedbugs use to identify their resting spot. This is not going to explain all of it, but basically we used a sequence of chemical and behavioral techniques to identify specific chemicals in that aggregation pheromone, or in that poo, sorry, that are attractive in order to put that into an effective attractant. And so here you can see the different peaks. Each peak in that graph basically represents a different chemical. And odor is like a fingerprint. And here you can see an example of a trap which contains the pheromone sachet. So the little white square there is the pheromone sachet, which releases the odor. One thing that's important when it comes to emulating odor is that you need a correct ratio. So those chemicals need to be released at the right ratio to each other to effectively emulate the natural pheromone. This trap will attract refuge-seeking bedbugs. It's not designed to compete with a human host. In fact, it works with the host. The host is the real, the big attractant. Bedbugs need that blood meal. So the trap goes either side of the head end of the bed. And then when the bedbug's antenna goes, or brain goes, I'm no longer looking for CO2. Now I'm looking for the aggregation pheromone, really specific receptor response. Will go then be searching for that aggregation pheromone. Seems to be particularly attractive to nymphs, so really effective for pre and post-treatment verification, and is ideal for low to medium level of infestation. When you've got lots of competing pheromones, so lots of bedbugs, then the radar, I suppose, that's being emitted from that trap is no longer quite as strong or as effective, so it would take longer to detect bedbugs. So how does scent science apply to pest detection? So that's coming back to the second point now, which is IoT sensing for detection. And I'm conscious of time a little bit, but every pest has a unique scent pattern. So coming back to this picture, thank you AI, basically, that helped me make this photo. It looks a little bit like a lineup of pests vaping, but it's meant to signal that each pest has a different complex odor blend. It's like a soup. And in fact, so it's like a fingerprint or a musical score even. So, and we've been learning those patterns in order to apply them to remote detection tools. You can't put a lead on a mosquito or a bed bug and dogs aren't quite as scalable as for remote detection. But we can create machines that can do this. And there are several types of gas sensors, for example, that already exist. So gas, odor is just a gas designed to detect CO2, for example. They're really good at picking up a single chemical, but odors are a mixture of chemicals, and the interpretation of sensor signal was impossible before. But what's been missing is a way to replicate that insect brain, and the answer is in AI. So we've been using AI to replicate neural networks found in insects' brains, essentially, to learn and process scent data. And with machine learning, we can now continuously improve the accuracy of detection. It works a bit like an insect brain, not quite as good, but we are getting there. At Arctech, we've developed a scent-enabled detection. So each target, in this case, a bedbug, is emitting the volatile organic compounds that are its odor, not just the aggregation pheromone, many different odors. These chemicals come into contact with a sensor array inside the IoT device, and that data is then transmitted to the cloud, where it's decoded using an algorithm that tells it that it's a bedbug or no bedbug, or in the future, bedbug or cockroach, for example. The great thing about this is that odor is so specific, it carries huge potential. Obviously, there's a little screen there saying that it sends an alert. That's really important that you get the alert. For rodent detection, for example, males will smell different to females, and pregnant females will smell different to non-pregnant females. And the opportunities are limitless, and the technology is closer than you might think. Remote monitoring, obviously, is incredible. It's had its ups and downs, and the technology is changing and progressing all the time. So whether it's via motion sensing or camera sensing or scent detection, it's going to become an increasingly important tool in the future of pest control. And that's because there's only one way we can really take control of this unpredictability. There's our friends there below, the problem children. Each device will provide a whole array of rich data, essentially. Data about where, when, what, and how many, which over time, which when combined with meteorological data and historic data, it will really enable us to better predict and prevent pest outbreaks. Thank you.
Amazing. Thank you very much. It was absolutely worth the wait. That's a really interesting topic. So thank you for going into such depth for
You're
um
welcome. I'm sorry, so sorry again about the technical issues, but yeah.
oh don't worry. If you'd seen my first ever webinar, you did substantially better than I did. And I'm sure the chat will attest to that for those who did watch me. So I have no questions at the moment, just an absolute outpouring of support though for your presentation. So thank you for that.
Good. Oh, you're
Um,
welcome. Yeah,
and then
absolute pleasure.
hopefully again, you'll be at Pestex as well, I believe. Yeah.
Will be. Yeah.
And when's the product coming to market, do we think? So,
Very good question. Months rather than years, but it
okay.
might be years for some. Depends. We are deep in our knees in field trial type work right now, so it won't be too long.
Wonderful. Well, we'll absolutely look forward to it. And again, thank you for coming on and joining us today.
Thanks for having me.